distance above and below. Okay, and they can be in the left plane, on the axis, or on the right plane. Okay, so let's look at each of them in turn. So if it's on the right hand part of the plane, then it's going to look like basically some a e to the sigma e to the j omega, okay, where this, so maybe I should call a plus ab, so e to the a, e to the a, j, b. And so this is going to look like basically, I don't know what I'm writing here anymore. Okay, e to the a, e to the jb. This is a pure complex value over here, jb, right? And so this is basically a sinusoidal oscillation. This is a phasor. E to the jb is a phasor, okay, of unit magnitude with some angular velocity given by b, okay? But from our perspective, it's all we care about is its magnitude is 1. It's a pure phasor, okay? So this one is going to have unit magnitude. E to the a is the real part of this complex conjugate root, whether it's on the left-hand side, on the axis, or over here, right? If it's on the left-hand side over here of the plane, like this blue, these two guys over here, then this is going to decay. So we're going to get an oscillation that decays over time, okay? And if it decays over time, the area under the curve of that oscillation is going to be bounded, which means that this is going to be bounded and we get BIBO stability. Okay. On the other hand, if it is going to be on the right hand side, this part is unit magnitude, this is some constant, and this value is going to keep increasing, so our oscillation is going to look like that. Okay, so they're going to unbound it and enlarge, okay, because it's an exponentially modulated oscillation, right? So we're going to get this kind of this helix really that goes on time, but at any rate it's going to be unbounded, so the area is unbounded. If the area is unbounded, this value is unbounded, and so yt is unbounded, it's not BIBO stable. Okay, what happens if you're on the axis? Well, in this case this value is e to the a is just 1, and so it just becomes some constant times this, so it's basically an oscillation that doesn't grow or shrink, it just stays oscillating all the time. If you look at the absolute value of this, it is actually going to grow to infinity. Okay, I mean in some sense this ratio, because it's absolute value, it is going to grow to infinity. So we could call it BIBO unstable. Some people call it marginally stable. The system is oscillating, right? And oscillations are not growing, they're not shrinking, they're just oscillating forever. In a real system, of course, it's going to dissipate. The oscillations will dissipate due to frictional causes and so on. But mathematically speaking, it's unbounded. Okay, so there is a kind of a ongoing, I would say, different textbooks have different notations. In some cases it's called unstable, some cases it's called marginally stable. So what I've tried to do is to consistently use the word marginally stable for complex conjugate roots on the j-axis. So the j-axis is the real axis, the imaginary axis. So if it's on the thing, call it marginally stable, and unfortunately it's a typo further down in the text, which I'll tell you in a minute. But it's up to you what you want to call it, right? Because in the actual system is going to be oscillating with a bounded value, and with this definition it's going to be going to infinity. Okay. So that's the case when you have complex conjugate roots, okay, and they're distinct complex, they're not repeated. Distinct meaning this, they're not repeated. Okay. So any questions about this? So the root gives us a quick picture into what the system is doing. If I see a picture with something over here, I know I have an exponential decay, and if I picture over there, it's going it's decaying even faster, right? So if I look at just these two x's, I say, oh yeah, sure, this has one root over here, one root over here, and then I can look at these, I can say it's going to be oscillating. I can look at the oscillatory frequency by just telling you how far it is off this over here. The larger the value of b, the faster the oscillatory frequency. Okay, because when b is 0, that means it's oscillating with 0 frequency. So the position of the roots is almost like an X-ray into the system. So somebody can give you a system and say, here's where the roots are. Okay, you can say right away, sure, it's going to have some transient response or whatever. So decay over here, and I'm going to some oscillations. The oscillations are decaying. This is a slowly decaying oscillation. That's a fast decaying oscillation, etc. So you're getting this insight right away into the notion of the picture. The final case is when you have repeated roots. Okay, so with repeated roots, we have to be a bit careful depending on where the exact position of the roots are. So, okay, so let me make sure I don't mess this up. So for repeated roots, I'm not going to go to the math, but basically you can say that the system is stable for repeated roots okay, it's a stable if and only if the real part of the root is less than or equal to 0. So we need the roots to be repeated. So if it's complex conjugate, then it needs to be on the left-hand side. So we typically show repeated roots something like this. There's an x and there's a circle. It means that one of the roots is the x of the circle. That's a complex conjugated repeated root with a real part in the left half plane. And this is kind of a repeated root that is real on the left-hand side, left half plane. So here we have got a system that's still stable. Okay. Repeated roots on the axis, which I'll draw like this. So this is a repeated root on the j-axis. Okay. And the complex conjugate means that it's going to be unstable. Okay. And you can actually see why if you do the time domain. And of course, anything to the right is also unstable. So this is the condition for system stability for repeated roots. The real part of the roots must be on the left half plane. Okay, it can't, even on the axis is actually not good enough. Okay, right, so where am I here? Okay, so we can summarize all this by saying that the system is stable if all the roots of the transfer function, okay, which is from here, are on the left half plane. If even one root lies to the right, then we're going to have this one going off to infinity. So that's a problem. Okay. If you have the conjugate pairs, then if the conjugate pairs are on the left-hand side, that's good. It's okay. If they're on the axis, okay, then if you have one pair on the axis, that's fine. It's going to be oscillatory. But if it's more than one pair on the axis, repeated roots on the axis, at the same points on the axis, then we get instability. Okay, so that's sort of the summary of all these, of how this works. Okay, so any questions about this? Okay, so we kind of, our main criterion really is to look for roots being on the left half plane. And if we find any kind of roots on the j-axis, we say, okay, is it only one set that's repeating, in which case it's marginally stable. And if it's more than one set on the same positions, then it's unstable. Okay, yeah?
Why is it, if there's more than one set, then it's unstable?
The way it works is that if you look at the, it looks like basically s plus j omega, okay, square, roughly, and then there's s minus j omega square, okay? So the so they'll look like a plus b over s plus j omega plus c over s minus j omega square plus d over s minus j omega. So this is roughly what it's going to look like, okay? The inverse Laplace of this is going to look like omega t e to the minus j omega t. So this t over here, okay, is going to make that absolute value over there go to infinity. So that's where the repeated roots are going to be a problem. Okay. Of course, repeated real roots are not a problem because the real roots on the x-axis are 0. E to the 0 is 1, so it goes away. It's just a complex conjugate once you have to worry about the inverse over here. So thanks to your question, I lost one final exam question. Okay. So I was going to set that in the final. Okay. Oh well. But you see what's going on? It's because of the transform of the, and of course if you do square, cube and so on, same thing, you get the same omega t squared, etc. just from that. It's just the Laplace transform doesn't work that way. Okay, so let me just do the homework example now, because now the homework example should be relatively easy to look at. Let's see, I'm going to do it here. So the beauty of this is we just take GS, and just from looking at the form of GS, we can pretty much tell what's going on. So in the case of the homework example, I said that G of S has a denominator polynomial. We don't even care what it is. It's something over 12s cubed minus 2s squared plus 4s plus 1. And so, you know, there are places on the internet where you can just type in a polynomial. It tells you what the roots are. And because root finding is a pretty well understood numerical algorithm, there's no need to know how it's done. It's fairly complicated. But at any rate, the roots are minus 0.204. And then it's a complex conjugate pair, which is 0.185 plus minus something. Well, we don't really care. We just care about the real part. The real part is on the right-hand side of the half plane. And consequently, this is going to be unstable system. Okay. So you can see how easy it is. We just write down, if you knew just the denominator part of the system, all we need to do is plug it in and we get an answer right away. It's unstable. Okay. One of the things that used to be very hard to do in the old days was finding roots of polynomials. If you have polynomial in the 15th degree or 20th degree, whatever, people just could not do it because they didn't have computers to do numerical recipes, right? So they would be very complicated. And so much of control theory developed into tricks to estimate where the roots would be. Are they going to be a left plane or right half plane? Because somebody told you, you know, if I told you this equation right here, this polynomial right here, there's no obvious way to know that's going to have complex conjugate pair which has a positive real, right? If I say, okay, what about this? I made this minus plus 10, I have no idea, right? And so you can imagine that a control engineer from the 1920s confronted by this would be really pretty miserable because they have no website to go to, you know, to go and solve this. And it's this is in order 3, so okay, that's fine, but I just made it order 6. Now they're in big trouble because there are no standard forms for, you know, order 6. Polynomials. Now we can just, as I said, use numerical recipes and computers to do it for us, and you know it's so easily available. I can just go plug this in, get the answer in a matter of seconds. So a huge amount of work was done in a thing called Nyquist plots and Bode plots and things like that. All of that was just trying to estimate where are these roots, because you don't know where the roots are. But we know where the roots are, so it's easy for us to do it, and that's what we do. Okay, so I have one more correction to make in the text. Example 17, I had given this, it's funny, I chose this example for instability, and then in the last minute I went and wrote the wrong thing. I have no idea why, and then I didn't catch it either. So here we have the denominator polynomial s to the 4 plus 50 s squared. It's something over this plus 625, and this is going to be, is nothing but more than s squared plus 25 square, and this is nothing more than s plus j5 into s minus j5 into, which is, and the whole thing squared. So if you look at it's basically repeated roots at j5 and j minus 5, and there's 2 of them. So this is an example of an unstable system. Okay, it's unstable because I have repeated roots on the real axis at plus minus j5, and so unfortunately in example 17 I wrote marginally stable. It is unstable, and in fact it's a classic unstable repeated roots on the complex axis. I don't know why I put that there. Okay, any questions about this so far? Okay, let me now look at that web server example, or maybe I should, actually I'm going to leave that to you to look at. Example 18, again, unfortunately, there is a mistake there, and the mistake is that for the differential, okay, Let me actually do it. It's actually relatively straightforward. Let's just look at the controllers for the proportional integral and derivative form. For the proportional controller, okay, for the proportional controller, we had g equals 1 over 1 plus s tau. And so the root is going to be s equals minus 1 over tau. Okay, and this is going to be always in the left half plane because tau is a positive time constant, right? Positive time. So this is going to be always stable. So that's good. Proportional controllers are stable. For the integral, we had g equals ki, for that's the constant ki, s square plus ki, and this is going to be, roots are going to be plus minus jki, which are essentially complex conjugate roots on the imaginary axis, right? And so this is going to be oscillatory. We already saw that. We already saw it was oscillatory. So that was, again, relatively easy. For the derivative mode, the example actually has a mistake. So I said y equals kd over 1 plus kd r. And I said that the root is positive. Well, in this case, there's no s. Okay. There is no s. This is just this y in this domain is basically function of this. So if you have if our input is 1 over s, then the value of s for which is this is 0. Okay, the root is s is infinite actually. Okay, we never actually have a system. There's no value for this for which yt is 0. So we can look at y is basically going to be the constant kd over 1 plus kd, right? Because the Laplace transform of 1 over s is the unit. So this is going to be the yt, the step response is going to be this. And for this, we know that the integral over there is going to go to infinity. So we could say, yeah, it's unstable, okay, because the integral of yt is going to be unstable. So we can... So I guess this correction is that instead of saying note that this is always positive, what I really meant to say is that yt is constant, okay, for the step response. And so we're going to get this the unit, this being the input, the bounded input, step input we're going over here. But any input, as long as it's bounded, will have some kind of fixed value like that. Yeah.
Sir, on the example on the left side,
yeah.
When s equal, the value, the roots are s is equal to plus or minus j5.
j5, right.
And you told that is unstable.
Well, it's squared. S plus minus j5 squared. Because it's s squared plus 25 squared. If it's just s minus plus minus j5, that would be oscillatory. But here it's squared. Otherwise, it would be okay. Yeah.
So
okay.
Oscillatory is like marginally stable.
Marginally stable, right? But as I said, in the definition of if you take the absolute integral of the absolute value, that's infinite, right? But in the actual system, so that's where it's a bit of a shady ground. Is it marginally stable or unstable? Okay, different people have to.
Should we like an example?
I'm calling it marginally stable, oscillatory, marginally stable. It's a bounded oscillation. It's an oscillation, but it's bounded. It's not growing without bound, right? So I call it marginally stable. Yeah.
What happens to the physical system?
Over here, with this one over here, it's going to be oscillatory growing, like that. It's going to be, and this envelope is going to be linear because it's omega t e to the j omega t, right? So it's going to be linearly growing envelope. So it's an amplitude. It's growing linearly, and that case is basically where we have a system like this. We have ys equals gs us, okay? And let's say that gs has something that looks like this, a over s plus j omega plus b over s minus j omega for the sake of argument. And as you know, this is going to look like basically some oscillatory response with if you look at the poles over here, they're going to be plus minus j omega. This is j omega, this is minus j omega. Now, here's the thing. let's say that u, which we had conveniently written as r max, as being some r max, actually also has the same value plus minus j omega, right? So we get repeated roots over here. Okay? Then y is, now to determine what y is, we need to know not only what g is, but also what u is for this special case. Okay? Because in this case, what's going to happen is that because these repeated roots overlap, we're going to get unstable behavior rather than marginally stable behavior. Okay? So is that clear what's going on? So in the earlier case, we said just forget about US. Who cares? You know, we just going to look at GS. But in the particular case where GS has complex conjugate roots on the real axis, or on the imaginary axis, like this, and US also happens to have in its transform the same complex conjugate pair, then instead of having oscillatory system like this, we get something like that. Okay? Is that clear? This is extremely important. And the reason is because this is actually the Tacoma-Narrows bridge. Okay? This picture right here is the Tacoma-Narrows bridge, believe it or not. Okay? Remember what happened over there? We had a system, which was the bridge, which had some oscillatory modes, which were these x's. Okay? The wind was blowing against it. Okay? If the wind were having a particular frequency which was not one of these frequencies, that would be fine. But when the wind has a frequency, because the wind has actually all frequencies in it, when the wind has a frequency which has the same frequency, the system which is having a bounded magnitude oscillation like this, it becomes this and the bridge collapses. Okay? So this picture is actually now like an X-ray into the Tacoma-Narrows bridge. Okay, and that's the beauty of it. From understanding so far, I can just draw this to you and say, sure, I have repeated roots on the imaginary axis, and GS has that one of these terms in its natural response. Because remember, the GS is the impulse response. It's a natural response. You just give it an impulse, and it says, yeah, I'm going to vibrate at this particular oscillatory frequency, j omega. And the wind comes in, and it has its natural frequencies as well. And when you have sufficient energy in that natural frequencies and sustained, okay, then these roots are going to come in, and we get collapse. Okay, and so it's kind of interesting to see that this little picture like this can explain a bridge collapse. Okay, and it follows from understanding what happens when you have repeated roots on the imaginary axis, which follows from the Laplace transform and all the other stuff. So what we're studying here really has some meaningful impact. The other case where this happens to have real meaning is radio receivers, right? When you have a radio receiver and you're receiving some radio signal, I guess most of you don't know what it means to tune. Do you know what it means to tune a radio dial? Okay, you have a dial, you turn it, right? So how many people have actually not done this? Turn a radio dial and listen to the radio. You just press a button, you get different FM frequencies. Okay, how many have not tuned a dial? Okay, good. So at least you guys are not that old. So when you're tuning a dial, is that you have a knob actually, and behind the knob is actually you have a what really is a variable capacitor. It's a bunch of plates that are arranged so that they intersect or not intersect. So when they intersect, you get a lot of capacitance. When they unintersect, they have less capacitance. So you have therefore a variable capacitance drawn like this. You draw like that, and then you have an inductor, which is a coil, and you have some battery, power source, whatever, like so. And this is the standard, what's called the LC circuit. And the frequency of resonance of this circuit, or the inherent natural frequency of this circuit, the pluses over here, correspond to the values of L and C. Now, L is fixed, C is varying, so you're basically tuning the resonant frequency, the natural frequency. And the radio waves are being broadcast from these radio towers. So if you look out, say if you go to Kitchener and you look out towards the west, you'll see this very, very tall mast. And that mast is putting out radio waves at different frequencies. And what happens is those frequencies, those electromagnetic waves are all around us. They're actually going right through you right now. And you're not able to detect them. However, when you set up this LC circuit like so, what's going to happen is that if it's energized by this particular radio signal, the amplitude of the output actually is large. Okay, so it gets no signal when you don't have the right input. When you have the right tuning frequency, you can actually pick up the signal across this, okay, across some resistor, some nominal resistor, and put it in a loudspeaker. And this actually is the simplest possible radio. Okay, I mean, I've left out many details, but basically speaking, that's what we're doing. We're tuning the resonance frequency. So the same phenomenon responsible for the loss of the Tacoma Bridge is also the phenomenon responsible for you to be able to listen to radio. And of course, for Wi-Fi communication, same thing. Okay. At the basic level, we're going to tune some receiver to receive signals, a carrier signal at some carrier frequency. You know, typically in Wi-Fi, it's 2.4 gigahertz, 2.42 something gigahertz, depending on the channel. And that's what's going on. We're picking up the carrier, and then we modulate the carrier using what we talked about earlier, you know, phase shift keying and amplitude keying and so on to send zeros and ones, and that's how all of Wi-Fi basically works as well. So it's all based on this picture right here. So even though it's a corner case, it's a very important case in terms of practical communication. Okay. Any questions about this over here? And it's beautiful. It just comes straight out of the Laplace transform. Okay, poles. So poles are the same as roots. So we already talked about that. Poles are just another way of saying roots. And the reason why we call it poles is because their roots are the denominator. So when the value of that value is 0, then the value of the function is infinite. It's like a pole going up into infinity. So it's just the roots of the denominator polynomial are also the poles of the system. Okay, so I'm going to start talking about Lyapunov stability. We just have a few minutes, so I'm not going to go too much into that. Actually, no, I have to talk about the zero input stability first. So far we've done basically BIBO stability, and I'm just going too early for this, so I should do zero input. So for zero input stability, I remember there's also a homework question on this. Yeah, we have a few minutes. Okay. So we're going to look at essentially the state space view of the world, and what happens is that in the state space view of the world, we have the state vector x, which is really a vector, and we worry about its state evolution, where x dot is the rate of change of state vector, written in the form of ax plus b u plus fw. It should be capital F, where f is diagonal. I said that earlier. And then y is the output. We don't really care about that. For zero input, we don't care about the disturbance, and we don't care about the input because the input is 0. So really all we're left with is x dot equals ax. That's all we care about. And now we want to know, for all possible values of x0, for all possible values of x0, we want x of t should be going to the 0 vector, where 0 is equilibrium position. That's what zero input stability means. Okay, and so for all x0, we want to do this. Now, in the case of the other representation, it's harder to talk about it, so I'm using this representation over here. So to study this, we just look at the Laplace transform. We get Sxs minus x0 equals axs, and so this gives us basically xs equals si minus a inverse x0. Okay, so how do we get that? Well, s times xs minus axs, we bring it to the other side, put x0 on the other side. And then remembering that A is a matrix, so we need to have Si minus A inverse x0 by pre-multiplying on both sides. We get this equation over here for xs. And we want to basically study what is going to happen to x t, okay, the time domain, because this is in the Laplace domain. And we got this basically by generalizing. I didn't actually, I'm just assuming that you agree that if x is a vector, the Laplace of a vector is the s times the Laplace of the individual components of the vector. So we're going to use that form. I haven't proved it, but it actually is true. So this over here, Si minus A inverse, can be written as C Si minus A transform by T. C is the cofactor over mod Si minus A, where it's A. This is the determinant over here. And this again comes from our study of determinants, where we remember that the inverse can be written as the cofactor over the determinant. And the cofactor is something we don't really care about, but this determinant over here essentially tells us what the system is doing. And this, if you remember your eigenvalues, is exactly the characteristic equation of the system. Okay, this determinant over here, the roots of this are in fact the eigenvalues of the system. Okay, Si minus A. And so we, of course, there we write like lambda I minus A, and lambda is the values of lambda for which determinant lambda minus A equals 0 are the eigenvalues. In the same case, the values of S are of course the eigenvalues of A. And so we can take any equation and just look at its characteristic equation and say basically how it's going to behave in terms of zero input stability. And so I'm just going to quickly do the homework example, because there we had x dot equals 3, 2, 2, 1, x plus something u plus something w. The u and w doesn't really care. All we care about this. So if you write Si minus A, you basically get S minus 3, 2, 2, S minus 1, which turns out to be S squared minus 4, S minus 1. And the roots are going to be S equals 2 plus minus square root 5. And 2 plus square root 5 is obviously going to be positive value. And it's and this is positive real value, and so it's unstable, okay, because 2 plus square root 5 is greater than 0. And when you have that, then you're basically out of luck. So this system is therefore unstable. Okay, so I've kind of run through this fairly quickly, and just so that I can get that answer out, I'm going to come back and probably discuss it in a bit more detail on Wednesday, but at least you should be able to turn your homework in for this time.